It's good to have you back once again. We have this topic of buoyancy and Archimedes Principle. In fact, the anchor here is Archimedes Principle, which we're trying to explore. So in this topic, you look at bodies that are immersed in water. What happens to them? Why is it that some sink, others won't? What makes some of them to float? So we'll look at those principles and see how it should make sense in that route. Let's get straight to the first part. So here, the first part to look at is what is known as the upthrust. If you look at this object, which is already in water, you can see this upward force. Let me just pick a pen quickly. This force acting upwards. This is the one we are calling the upthrust. With it, it's simply an upward force experienced when you put a body in water. In other words, when you take an object, put it not only in water, but in any liquid, the upward force that is experienced is the one we call the upthrust. And it even has a lot of sense when you look at some of the biggest animals that are alive on Earth. They are in water because they enjoy the assistance from this aspect here, the upthrust. Others, in other books, you'll find it written as the buoyant force or force of buoyancy. Now, that is up when you now take it further to Archimedes' principle. In Archimedes' principle, we're now trying to apply this same principle, the same aspect of the upthrust. Now, what this man did with his experiments, he actually came to discover that when you put an object in water, that upthrust to experience is supposed to be equal to the weight of the liquid it's able to displace. Meaning that if I take an object and put it in a liquid, a certain volume of liquid will be displaced. Now, it's not about the volume, it's about the weight of that quantity of the liquid which has been displaced, which gives us the value or the magnitude of the upthrust. That's according to Archimedes. Now, with him, it means that if this weight is lower than the upthrust, then the body is going to float. But if the weight is much higher, then you expect it to sink. It's as simple as that. What about flotation? Of course, this is like we can see just the tendency of the body to float. The height of that body which is immersed in the water is the one we call the draft. Then looking at buoyancy, it's just the tendency of a body immersed in a liquid to be lifted up or to be buoyed. It's just another term there, which is more of a tongue twister. Now, what about this, the aspect of floating and sinking? In simple terms, an object can only float if the upthrust is higher or equal to the weight of the body of that same object. But if the opposite is true, meaning the object has a weight which is bigger than the upthrust, then you expect it to start sinking. Now, the quickest way you can look at it is if you look at the overall density of an object, meaning even if you have air spaces in that object, put them together, come up with the overall density that it will have. So if you look at the overall density that it's going to have, if that density is lower than that of the liquid or almost just equal, then it's going to float. But if the density is much higher, then it's going to sink. Look at this example we have down here. Just get to look at this diagram. The first diagram there in the first picture, these are objects which are much, when you put them in the water, the total weight is too low compared to the upthrust they experience. They trap a lot of volume, and in the end, the upthrust that ends up acting on them is much higher than the weight. So they float. But some of them, if you look at their overall density, it's much lower than that of the liquid. That's why they're able to float like that. Look at this other team here. Solids, different materials with different densities, all of them, they were able to sink below this free surface because their overall density was much higher than that of the liquid. Well, that's just another interesting part about floating. So if you want to experience or to determine whether your body is going to float or sink, you can start from there before you can now go into the deep analysis of the upthrust and the weight, how they are behaving. Well, this is a practical kind of a topic. So let's straight away sample the first example. This is our first example. According to this one, the question is saying we have a vessel immersed in a liquid whose density is 900 kg per cubic meter. If the volume of the liquid it displaces is 52 cubic meters, calculate the weight of the vessel. Now let's just collect a bit of some data here. We have the density of the vessel, which is 900 kg per cubic meters. Then we have the volume of the liquid displaced. We'll call it VL, just like that. Then the specific weight of the liquid, we convert mass density to that by multiplying density multiplied by acceleration due to gravity. That is what gives us the specific weight. So that's what you're seeing there, 900 kg per cubic meter multiplied by 9.81. This is the answer we find. Now let's get to work then. The first thing we need to calculate is the upthrust. We said that the upthrust is normally equal to the weight of the displaced liquid. So the weight of the displaced liquid is supposed to be the product of the specific weight of the liquid and the volume of that same liquid. Let me go back again. The upthrust is equal to the weight of the displaced liquid. So what do you do to get that weight? You should multiply the specific weight of the liquid by the total volume of that same displaced liquid. Then the units will cancel out because this is in newtons per cubic meter. Then you are multiplying by a volume which is a cubic meter. This will cancel. That will cancel with that. So in the end, you just end up with a Newton, which is a force. So that's why we are saying the upthrust is equal to specific weight multiplied by the volume. And that's the answer you get, 8829 multiplied by 52. So you have 459,108 newtons. So here, we are saying summation of upwards forces is equal to summation of downwards forces. The upwards forces is just the upthrust. The downwards forces is just one force. It's the weight. That's what we're talking about. This is the weight, and that's the upthrust. And they're in balance. Now we can just substitute the weight. Where there is upthrust, we put this number here, and that's what we find. So the weight of this body is 459,108 newtons. So that's how you get to this simple question. Now let's make progress. What if we decide to give it a different setup where you're given the dimensions of this object? From there, you should be able to calculate the weight. And at the same time, you're also given, or you're required to find also the draft, the one we talked about, this height here. How can you go about it? Example 2. So in this example, we're looking at a vessel or just a block whose dimensions are 2 meters by 1.5 by 1 meter. The density of this vessel is 600 kg per cubic meters. And the vessel is immersed in water. The density of this water, 1000 kg per cubic meter. You have to remember here that we will not always need to give you this. It's a standard liquid. Its weight, its specific weight is 9810. Its relative density is 1. The density is 1000 kg per cubic meter. Relative density and specific gravity, both of them 1. So we are required now to calculate the weight of the vessel, the volume of the water displaced, the draft of the vessel, and the force required to submerge the vessel completely in the water. Let's collect the information provided. First, the volume of the vessel is a product of this length, width, and height. So 2 by 1.5 by 1. And that's the answer you get. Specific weight of the vessel, we just multiply. This is 600 kg per cubic meter. Here, the secret is you want to convert this kg to newtons. How do you do it? There. Remember from the properties of these liquids or the properties of fluids. Oh, sorry, not this one. Let me just clear that, or maybe we can ignore it. We're saying if you want to find the specific weight, you normally say it is equal to the density of the liquid, and then you multiply it by gravity, acceleration due to gravity. It's as simple as that. Now here, that's what we've done, 600 kg per cubic meter, multiplied by 9.81. Then that's your answer there. Specific weight for the pure water, we have this 1000. Then we're multiplying it by 9.81. That's the answer there, 9,810. Let's get to the first part. To get the weight of the vessel, we go back to balance. Here we've already been given the specific weight of the vessel and the total volume of the vessel. So it's straightforward. You just multiply the two values. It will give you how heavy this object is. And so there we are. We're multiplying 5886. This is the specific weight of the vessel by the total volume for the same vessel, which is 3. When you multiply, that's the answer you get, 17,658. The second part was asking for the volume of the water it's going to displace. So here we assume that you take this vessel, you put it in water. Is it going to sink? We've already said if you compare the vessel is only having density of 600 kg per cubic meter. And then you've put it in water, whose density is 1000 kg per cubic meter. So you don't expect it to sink because the weight, rather the density of the vessel is lower than the density of the liquid. So it remains afloat. If it's going to float, then how much liquid, how much water in this case is it going to displace? So balancing the forces, that's how they behave. We just have the upthrust and the weight. So expanding, you have specific weight of the water times the volume, they give you the weight of the vessel. When you substitute, we've already been given the weight, which is 17,658. We just calculated this one. Specific weight of the water is 9,810. Then we're looking for this volume here. Making it the subject means you can divide through by the same 9810. Divide here by 9810, and on the other side, the same thing. That's the answer you will find, 1.8 cubic meters. What about the draft? For the draft, you need to multiply the volume of the liquid displaced, which is this, is equal to base area times the draft, or length times the width times the height. In this case, the height is the draft. The volume of the water displaced is this 1.8 as we calculated it there. Here you need to be very careful, because if you just proceed to the next part, if this is wrong, then you expect everything coming down there to be wrong as well. Because you can imagine, we used this in here, and here we're looking for the draft, so we substituted right there. Length, width, and height. Length, width by the draft. So make your draft the subject. There you are. That's how it should be able to make sense. That is your height immersed in the liquid. And that is the answer you find. The last part of the question was asking for the force required to cause this whole thing to sink in water. Again, the principle comes there. How are we going to help it to sink? Introduce a force here. This force F is the one that is going to force it to go deep into the water, and it remains there. So summation of upwards forces is equal to the summation of downwards forces. The upwards forces is just this one, the upthrust. Downward forces, we have the weight and the force F. So the next part is just to substitute. But remember, if you compare the two, in the first case here, the body was floating. Here, it is sinking. The volume of the liquid displaced cannot be the same. When it sinks in water completely, it means the amount of liquid it's going to displace should be equal to its total volume. That's why here we are using this volume of water displaced. We should use the total volume of the vessel, the 3. Here, of course, we shall maintain. Remember that for the upthrust, we want to find the weight of the displaced liquid. So we multiply the specific weight of the same water by its total volume. Then you have weight plus that. Great. Now with that, we're saying 9,810 is the specific weight of the water. Then we're multiplying it by 3, which is the total volume of the liquid. Equals, then you have this 17,658 added to F. So let's make F the subject. It will mean you just divide both sides by the same, and that's what you're going to find. 1,172. 11,772 newtons. It was funny. Might have missed some numbers. So 11,772, and like usual, please, in case you see that the numbers are different, when you enter them in your calculator, you can always alert me so that we continue refining our document there. Thank you very much. Please go ahead and deal with the exercise here. It already has the answers, so you can measure and take note of your progress. Thank you. We'll link up in the next lesson. This time around, I think we can now go to fluid dynamics or fluids in motion. That will be our next lesson. Thank you.